Welcome to the AI Coach by Anil Nathu. Today, we're embarking on a really crucial deep dive. We're looking into a challenge that's, well, it's rapidly intensifying in the world of large language models, or LLMs. Researchers are calling it the prompt tax. And, this isn't just some abstract academic idea. It's a very real computational cost. And it's also about the increased latency, the waiting time that comes from feeding these, well, increasingly large and complex input prompts to these incredibly powerful AI models. It's becoming a fundamental roadblock, potentially preventing LLMs from powering truly real-time, large-scale applications out there in the real world.
It's absolutely right. It's a major hurdle. I mean, while these LLMs, like, the famous GPT-4, they are incredibly versatile, super powerful. They can handle everything from drafting really eloquent reports to generating complex code, even helping out in tricky areas like incident management. But their optimal performance, getting the best out of them, often hinges on providing them with just tons of context, extensive context.
Right, like giving someone really detailed instructions.
Exactly. Think of it like a highly skilled apprentice, right? The more detailed instructions and background info you give them, the better and more accurate their work usually is. But like you said, this comes at a significant price. Longer prompts mean higher processing costs for every single query you send, and, crucially, slower response times. Waiting longer for the answer. This is precisely where the whole idea, the innovation of prompt compression, steps in. The goal is to dramatically lighten that computational load, make it cheaper and faster, without sacrificing the quality or accuracy of the LLM's output.
And that's our specific mission for this deep dive today. We're going to unpack a truly novel method that's, well, it's making waves. TACO-RL. It's an intriguing acronym, right? It stands for Task-Aware Prompt Compression Optimization with Reinforcement Learning.
Quite a mouthful, but descriptive.
It is, and this groundbreaking work comes from a team of really brilliant Microsoft researchers, Shivam Shandilia, Menglin Xia, Supriyo Ghosh, Weikong Juzang, Qianhui Wu, and Victor Rule. Their method offers what seems like a significant shortcut to optimizing LLM performance. They're showing a way to dramatically cut down prompt size and get this, not just without sacrificing accuracy, but sometimes even improving it.
Which is pretty counterintuitive, but that's what the results suggest.
Exactly. And this pursuit of advanced practical optimization, well, that's precisely the kind of cutting-edge research we love to explore here on the Deep Dive. This is brought to you by the AI Coach by Anil Nathu, all to ensure you have the edge in understanding and deploying the most efficient AI applications out there.
Indeed. It's really about moving beyond just small, incremental gains to fundamental shifts in how we approach efficiency with these models.
So to really get why TACO-RL is such a big step forward, we need to first understand this, well, fascinating paradox that's emerged as LLMs have just exploded in popularity. It feels like just yesterday these models were mostly a curiosity, right? Something kind of confined to research labs.
Definitely. The pace has been incredible.
But now, as noted by influential work like Brown et al. Back in 2020 and Chowdhury et al. More recently in 2023, LLMs have surged into mainstream use. And for an astonishing range of tasks. We're talking about everything from really sophisticated, nuanced question answering, the kind that needs deep contextual understanding, to robust code generation for software development, and even automating aspects of complex tasks like, say, enterprise-level incident management. They've become, in a remarkably short time, pretty indispensable tools across loads of different industries.
Absolutely. And a huge part of that impressive rapid evolution in LLM effectiveness, it comes directly from the ingenuity of prompt engineering.
Yeah.
And, the rise of these advanced prompting techniques, we've seen methods emerge like in-context learning or ICL.
Right, ICL. That was from the original GPT-3 paper, wasn't it?
That's the one pioneered by Brown et al. In their foundational 2020 paper. With ICL, you essentially give the LLM a few examples, like desired input-output pairs right within the prompt itself. The model then learns from these examples on the fly without needing traditional heavy fine-tuning. But here's the catch, the trade-off. Each of those examples, each demonstration of how you want the model to act, well, it adds to the prompt's length. You're effectively packing a mini data set into every single query you make.
Okay, so that's one way prompts get longer. What else?
Well, then there's chain of thought prompting, TAT. This technique was really highlighted by Wei et al. In 2023. This is where you guide the model through a step-by-step reasoning process. You explicitly show it how to break down a complex problem into smaller, more manageable parts. You're literally asking the model to think aloud within the prompt, generating this verbose, intermediate thought process before it finally arrives at the answer.
Which is great for complex problems, I imagine.
Incredibly powerful for complex reasoning, yeah. But that intermediate thought process, just by its very nature, it generates and requires significantly longer prompts. It adds a lot of text.
Makes sense. And the third big one.
And of course, a really transformative technique has been retrieval augmented generation, or IA, introduced by Lewis et al. Back in 2021. RA systems are clever. They pull in external, highly relevant knowledge, maybe from databases, internal documents, or even the live web, and they append it directly to the LLM's prompt. This informs its response, grounds it in facts.
Ah, so that helps with accuracy and staying up to date. Reduces hallucinations too, right?
Exactly. It's brilliant for grounding the LLM in, say, up-to-date information or proprietary company knowledge, and it drastically cuts down on the model just making things up. However, that external knowledge often involves significant chunks of text, sometimes huge chunks. This adds substantial length to the prompt just to provide the necessary context for the LM to work with. So what's truly fascinating and kind of paradoxical is how these techniques, ICL, COT, RAG, while they undeniably enhance LLM performance, making them way more nuanced and accurate,
Yeah.
they inherently lead to longer and longer input prompt context lengths. They demand more data, more context to perform at their best, really pushing the boundaries of what's practical from a cost and speed perspective.
And that's where the paradox really hits us, isn't it? These incredibly powerful techniques, the ones making LLMs more capable than ever, simultaneously introduce this critical bottleneck. We're talking significantly higher inference costs. It costs more money to run each query and increased latency requirements. You wait longer.
Precisely. It's a direct trade-off.
Imagine trying to build, say, a real-time conversational AI. Maybe for a critical application like healthcare diagnostics or financial trading advice. Places where every second of delay could cost millions or potentially worse. And every query takes precious seconds, maybe even minutes, because the prompt is just enormous.
Like simply not practical, not scalable.
No, not for many real-world, high-throughput LLM deployments. This prompt tax, as they call it, becomes a very real, very significant barrier. It hinders widespread adoption and responsiveness. It's a problem that urgently needs solving for the future of AI, wouldn't you say?
I couldn't agree more. And the researchers behind TacoRL, they really highlight this core problem. They do it by thoroughly detailing the limitations of the existing prompt compression techniques, the ones that came before.
Okay, so what were people trying before taco
Well, for instance, some earlier approaches fall into the category of task-aware compression models. A notable example they mention is the work by Zhuang et al. In 2024. These models typically involve fine-tuning a whole separate, dedicated task-specific decoder model. So a model specifically trained just to summarize or compress for one particular goal.
That sounds specific and maybe slow.
Well, theoretically promising, right,
It-
because it's tailored to the task. But the paper explicitly states this approach leads to high inference latency and cost. So yes, while it might be accurate for its narrow niche, it's highly inefficient. Too slow for broad application across many different tasks or in situations needing rapid responses. It's like having, I don't know, a custom-built, incredibly precise machine that just takes too long to operate for any kind of high-volume production.
Okay, so task-aware, but too heavy-handed, too specialized, too slow for general use, even if they're accurate in their niche. Got it. What about the other side?
You've got it. Exactly. So on the other end of the spectrum, you have what are called task-agnostic compression models. These include methods like those proposed by Zhang et al. In 2023, Li et al. In 2023, or Pan et al. In 2024, whose work TacoRL actually built upon, which we'll get to. These methods try to compress prompts without specific knowledge of the particular task the main LLM will perform afterwards.
How do they decide what to cut then?
Well, they might remove tokens based on sort of suboptimal metrics, like information entropy, basically, how much surprise or statistical uniqueness a token holds in isolation. Or they might train supervised binary token classification models. These just learn whether to keep or discard a token based on general patterns they've seen in lots of text. The key critique from the TacoRL paper is blunt. These methods fail to capture task-specific behaviors.
Meaning they don't know why something is important for this specific job.
Exactly. They don't understand why certain pieces of information might be profoundly crucial for task A, but maybe less so for task B, even using the same base text. This often leads to important details being just indiscriminately discarded, like someone quickly skimming a report and just removing sentences they think are unimportant without fully grasping the underlying context or the reader's specific need. So you end up with this dilemma. Either you get highly efficient but potentially inaccurate compression, or You get highly accurate but inefficient and slow compression.
Mm.
Nothing quite hits that sweet spot of being just right.
It sounds like a real Goldilocks problem, doesn't it? Nothing is quite right.
Oh,
This
wow.
perfectly sets the stage for the core research questions that Taco RL was really designed to tackle. The researchers laid out two fundamental questions they wanted to answer. First, how do we design a prompt compression model that effectively leverages bidirectional context, meaning it understands the full nuance of how words relate to each other, looking both forwards and backwards in the text,
Right, like how humans read.
and crucially provides low inference latency. It needs to be fast. And second, how can we efficiently train such a model? How can we guide it properly using task-specific reward signals to minimize the computational cost when we want to adapt it to new tasks?
These are the big, critical questions.
They really are. And as we'll see, the answers they found have massive implications for how we deploy and scale LLM applications in the future. This kind of problem solving is something the AI Coach by Anil Nathu platform constantly emphasizes finding efficient, practical solutions.
Definitely. So to address these crucial questions and finally break this efficiency paradox, TacoRL emerges as a, well, truly breakthrough solution in my view. The authors introduce it as a method that uniquely combines two key things: a latency-aware encoder-based transformer model, that's the fast part, with an on-policy reinforcement learning algorithm, that's the smart part.
Okay, encoder for speed, RL for smarts.
Exactly. The core innovation here, as the researchers describe it, is guiding a fine-tuned generic encoder model with task-specific reward signals. So instead of relying on predefined rules or general models that don't really consider the specific task downstream, TacoRL learns to compress based on how well the compressed prompt actually helps the LLM achieve a specific task goal.
Ah, so it's judged on the final outcome.
Precisely. It's a
Yeah.
profound shift. It's optimizing for what really matters.
Okay, let's unpack this a bit more. So it's not starting completely from scratch, right? You mentioned it builds on existing work. The paper specifically mentions LLM Lingua 2 by Pan et al. In 2024. How does that existing work set the stage for TacoRL, and what makes TacoRL truly unique then?
That's a really perceptive question.
Yeah.
So LLM Lingua 2 established a strong and, importantly, efficient foundation. It used an encoder-based transformer, similar to models like BERT, for binary classification of input tokens. Essentially, it was trained to make a very simple, very fast decision for each token: keep or remove.
Okay, quick yes/no for each word.
Pretty much. This provided a quick, efficient way to compress prompts, but in a largely task-agnostic manner. It didn't really know why it was keeping or removing, just based on general patterns. TacoRL takes that efficient base, that fast decision-making engine, and injects this layer of deep intelligence and purpose. It effectively answers that first research question about low inference latency by leveraging that very encoder-based structure. It's inherently designed for speed because it's just classifying existing tokens.
Right, it's not generating new text or anything complex.
Exactly. It's not generating new text or complex summaries like those older task-aware decoders. This makes its compression almost instantaneous during use.
And this is precisely where the reinforcement learning aspect comes in, making it truly novel and task-aware. The paper specifically mentions using the lightweight reinforce algorithm, a classic method from Williams's 1992 work. Can you elaborate on how RL, particularly this on-policy approach, helps the model learn to be task-aware? How does it differentiate TacoRL?
Certainly. So reinforcement learning, at its heart, it's all about learning through trial and error, right? Guided by a system of rewards and penalties. In the context of TacoRL, it works in this fascinating iterative cycle. Imagine the compression model, the encoder, as an agent. This agent makes a compression decision on an input prompt. It acts by deciding which tokens to keep and which to discard.
Okay, it tries compressing the text.
Yep. The resulting compressed prompt is then fed to the target LLM. They use GPT 3.5 Turbo for evaluation in the paper, a relatively cheaper but still capable model. That LLM generates an output for the specific task at hand, say a summary or an answer to a question. Then, this outcome from the compressed prompt is meticulously evaluated against the output produced by the original uncompressed prompt for that very same task.
Comparing the results from the short version and the long version.
Exactly. Now, here's where the task-specific reward signals really come into play. These rewards are directly derived from this comparison. If the compressed prompt leads to an output that is sufficiently similar or accurate for the task, for example, if a summarized output retains key information, or a question answering output is correct, the compression model, our agent, receives a positive reward. Good job. If, however, the compression leads to a poor or incorrect output, it gets a penalty. Try again.
Okay, learning from feedback.
Critical feedback, yes. And the on-policy aspect of the reinforced algorithm means the model is constantly learning from its own experiences. It tries a compression strategy, immediately sees the outcome, the reward or penalty, and then adjusts its strategy based on those specific actions it just took. It's like a chef refining a recipe by tasting it right after each little tweak, rather than waiting for external reviews or just following general culinary advice.
That's a great analogy. Direct, immediate feedback.
Right. This iterative self-correcting process, guided by the lightweight reinforced algorithm, allows TalkRL to continually refine its encoder's parameters, the weights inside the model. It literally teaches the model to make smarter compression decisions over time, optimizing directly for performance on the actual downstream task,
Hmm.
rather than just relying on general metrics or, heuristic rules of thumb. This is a critical step in making LLMs not just efficient, but smartly efficient for real-world applications. It learns what matters for the job.
Now let's really get into the nuts and bolts, because that's where the true genius often lies, right? The TagRL framework has three incredible clever key components that work together seamlessly, forming this intelligent compression engine. Let's start with the first one, the encoder model and action sampling. So for any given input prompt, how exactly does this encoder decide which tokens are essential enough to keep and which can be safely discarded?
Okay, so at its core, the encoder operates as a policy. Think of it as a decision maker. It's designed to predict probabilities for preserving each individual token in an input prompt, which we can call X. Imagine your prompt as a sequence of tokens by 1, by 2, by 3, and so on, up to xn. For each one of these tokens, the encoder outputs a probability, let's call it pi, the likelihood that this specific token should be kept.
So a score for each word, basically.
Essentially, yes, a preservation score between 0 to 1. Then the decision during inference, when you're actually using the model, is binary and remarkably straightforward. If the probability pi for a token is 0.5 or greater, the token is kept, we assign an action AI equals 1. Otherwise, if the probability is less than 0.5, the token is deemed discardable and AI equals 0, 1. It's out. The actual compressed prompt XC is then meticulously constructed using only the tokens that were ultimately retained, the ones with AI 1.
Simple thresholding, and how do they measure how much it's compressed?
Right, to quantify the efficiency, they use two key metrics. First is the compression rate, often denoted by the Greek letter pau, is simply the length of the compressed prompt divided by the length of the original prompt. So XCX of zero point 0.5 means it's half the original length. And then often more intuitively, they use the compression ratio, CR, which is just the inverse, 1. So a 2x compression ratio means the prompt is half its original size, 0.5, while a 6x compression ratio means it's 1/6 the original size, x for 0.167. Higher ratio means more compression.
Got it. Compression rate is the fraction remaining. Compression ratio is how many times smaller it is. And the paper specifically emphasizes the use of bidirectional context in this encoder, citing that foundational work by Devlin et al. From 2019, which introduced models like BERT. Why is this bidirectional context so crucial here, especially for something as nuanced as deciding which word to keep?
That's an excellent point to highlight. It's really key. Bidirectional context, as pioneered by models like BERT, and used here in the Columnar BERT, a large encoder, it means the encoder doesn't just look at the words that came before a given token when deciding its importance. It also simultaneously considers the words that come after it. And its position within the entire prompt structure matters too.
So it sees the whole picture for each word.
Exactly. Think of it this way. If you're trying to understand the importance of a single word in a sentence, say the word bank, its meaning and importance change drastically depending on the context. Is it riverbank or money bank? If you only read left to right, you might misunderstand or misjudge its importance before you see the later words. Or imagine a long sentence where a word at the beginning is defined or clarified by something way at the end. A unidirectional model might miss that connection.
Right, it wouldn't have seen the end yet.
Correct. Unlike older unidirectional models, this bidirectional view allows for a far more nuanced, holistic, and, well, intelligent understanding of each token's relevance within the entire prompt. It's not just about what a word means in isolation, but how it interacts with its surrounding words and the overall structure to contribute meaning for a specific task. This holistic view is absolutely crucial for identifying the truly essential information to retain and figuring out what can be safely removed without losing critical meaning. It makes the decision about what to keep much, much smarter than a simple left-to-right scan could ever be.
Okay, that makes perfect sense. Bidirectional context gives it a much richer understanding. So that covers the encoder and how it smartly generates the compressed prompt using this context. But how does TalkORL know if that compression was good? Was it a useful compression? This brings us right to the second key component, which is really the heart of the reinforcement learning process, the task-specific reward signal computation. This is where the model gets its crucial feedback. How is this reward actually calculated, and what guides it?
Right? The reward signal is the engine of the learning. For the reward calculation, the researchers made a very practical and clever choice. They use a relatively cheaper LLM model, specifically GPT 3.5 Turbo, as the proxy, the judge, for evaluating the compression quality. This model, GPT 3.5, generates outputs from both the original uncompressed prompt, let's call that YORIG, and the newly compressed prompt from the encoder, YICOMP. The reward, R, is then computed using a carefully chosen task-specific metric M, which we'll definitely detail more in a moment because it's super important. This metric M essentially measures the divergence, or maybe more accurately, the similarity between YICOMP and YORIG.
So how close is the answer from the short prompt to the answer from the long prompt?
Precisely. The core question being answered by the reward signal is how close is the output generated from the compressed prompt to the output generated from the original prompt, specifically for the given task. The higher the similarity, according to metric M, the greater the reward R. Simple as that.
Okay, but what about controlling the amount of compression during training? Does it just try to make the answers similar regardless of length?
Good question. What's also incredibly clever and robust about this design is the built-in penalty system. This helps guide the training process effectively towards the desired compression level. A negative constant reward, let's call it AJO would, is applied if the compression divergence, denoted as delta, falls outside a predefined tolerance threshold, L. This I is calculated simply as the actual compressed length minus the desired compressed length. That desired length is calculated as C times the original length, so AGUA EC AJX.
Okay, C is like the target compression factor.
Exactly. We'll talk more about C and L, but this penalty ensures that the model doesn't just maximize the task-specific reward, similarity of answers, but also tries to stick close to the desired compression ratio during training. It makes the learning process much more stable and focused. It acts like guardrails, keeping the compression length roughly where you want it while it learns the task.
So let's zero in on those two important parameters you just mentioned that control this process. The compression flexibility controller, C, and the tolerance threshold, L. Can you clarify their roles a bit more? How do they influence that trade-off between prompt length and output quality, especially during the training phase?
Certainly, they're crucial tuning knobs. The compression flexibility controller C is a turnable hyperparameter that you, the user or researcher, set before you start training the TalkORL model. It represents your desired proportion of tokens to retain from the original prompt. For instance, if you set C to 0.5, you're telling the model, hey, aim for roughly a 50% compression rate, which corresponds to a 2x compression ratio. A smaller C, say 2.2, means you're pushing for stricter compression, trying to retain only 20% of the tokens, a 5x ratio. A larger C, like PME 0.8, allows more tokens to be preserved. The C value provides crucial flexibility. It lets practitioners explicitly control that quality-cost trade-off during the training phase of TalkORL. It guides the learning.
But does the final compressed prompt always exactly match C?
That's a key distinction. This Matorazeyu primarily guides the encoder during training to learn optimal compression strategies around that target. During inference, when you're actually using the trained model to compress new prompts, the model is designed to always satisfy the exact desired compression rate you specify at that moment. It does this simply by selecting the tokens with the highest predicted preservation probabilities until it hits the target length. So C shapes the learning, but inference gives you precise control.
Okay, TAD-C guides training, inference enforces the exact rate. What about L, the tolerance?
Right, the tolerance threshold, L. This parameter addresses a very practical challenge in reinforcement learning, especially with probabilistic actions. Because the policy is unconstrained and actions keep or move are sampled based on probabilities, the exact target compression ratio C might not always be met perfectly during every single training step. Sometimes it might compress a bit more, sometimes a bit less, just due to the randomness. L allows for a small window of flexibility around that target compression length, Cx. If the actual compression divergence of the difference between the current compressed length and the target length falls within the range, L, meaning it's acceptably close to the target.
It gets the real reward based on the task.
Exactly. If it's within arrow L, the positive task-specific reward R, based on the output similarity, is propagated back to the model for learning. However, if the compressed prompt is either excessively short or unnecessarily long compared to the target, meaning A falls outside this RL range, then that constant negative reward R0 is immediately applied instead. This mechanism is vital. It stabilizes the compression process during training. It gently guides the model towards generating prompts of the desired lengths without unduly penalizing minor random fluctuations during learning.
So it stops the model from straying too far off the target length during training.
Precisely.
Right.
It keeps it focused. And crucially, as I mentioned, during actual inference time. You bypass this training mechanism, and the model ensures the exact compression rate you specify is always satisfied by taking the top probability tokens. L is purely a training aid for stability.
That's a really sophisticated way to balance the training goals, aim for the target length, but focus the learning on the task quality when you're close. This brings us neatly to the third core component, policy optimization using on-policy RL, specifically the reinforce algorithm. We've touched on how the rewards are computed, but how does all of this feedback, this reward data, come together to actually refine the model's compression strategy? How does it actually learn and get better over time?
Right, closing the loop. So with these task-specific reward signals are computed for each compression attempt, the classic reinforce algorithm comes into play. This algorithm, first introduced by Ronald Williams in his seminal 1992 paper, is what's used to update the encoder's policy parameters, the internal knobs and dials of the model. It's an on-policy gradient method. On-policy means it learns directly from the experiences, the compressions, and the resulting rewards generated by the current version of the policy, the current state of the encoder. It's continuously refining its own decision-making based on the immediate outcomes it observes.
Learning from its own actions, essentially.
Exactly. The underlying loss function used for this optimization is specifically designed to incorporate several critical elements to make the learning effective. First, obviously, it includes the reward itself. That's the direct signal of how good the compression was for the actual task. Higher reward means do more of that.
Yeah.
Second, it uses the log probability of the actions chosen by the encoder, the probability of keeping or removing each token. This mathematically guides the model to increase the probability of actions that led to higher rewards in the future. And third, critically, it includes something called Shannon's entropy regularization term, represented as EHP.
Entropy regularization, what does that do?
This EHP term is absolutely crucial for stable and effective RL training. It essentially encourages exploration during the learning process. It prevents the model from becoming too rigid or too confident too early in its compression decisions. Think of it as adding a bit of randomness or curiosity. Without it, the model might quickly find a compression strategy that works okay and then just stick with it, converging prematurely to a suboptimal solution, what we call a local minimum. It might miss a much better strategy it hasn't tried yet.
So it keeps the model from getting stuck in a rut too early.
Precisely. By encouraging a bit of exploration, it helps balance maximizing the immediate reward, exploitation doing what works now, with ensuring the model doesn't get stuck and keeps searching for potentially even better unseen compression options, exploration. Through this iterative optimization process, calculate reward. Use reinforce with entropy regularization to update parameters the encoder's ability to retain the truly essential task-specific information while aggressively minimizing prompt length is continually refined. It's a dynamic, self-improving process that consistently seeks the optimal balance between compression and task performance.
So summarizing the overall approach, which the paper refers to simply as Algorithm 1, it sounds like a remarkably robust and iterative cycle. It starts with an initial, perhaps task-agnostic or generally pre-trained encoder, then it repeatedly generates compressed prompts based on its current policy. It feeds those to the target LLM, gets outputs, meticulously determines the task-specific rewards by comparing outputs, and then, crucially, uses reinforce to update the encoder's policy parameters based on those rewards over multiple epochs or training rounds.
That's the loop, exactly.
This systematic, robust, and self-correcting process. Well, it's exactly why platforms like the AI Coach by Anil Nathu recommend digging into these deep learning methodologies for achieving cutting-edge AI performance. It's not just a simple trick, it's a continuous, intelligent feedback loop that truly drives both performance and efficiency gains.
Absolutely. And what's truly effective about Taco RL, the thing that's central to its task-aware nature that really sets it apart, is its intelligent ability to define and then dynamically utilize specific reward functions tailored for different types of LLM tasks. This isn't a one-size-fits-all approach trying to force a single metric onto every problem. No, it's about understanding what good actually looks like for each distinct application. summarization, QA code, and optimizing directly for that specific flavor of success.
Okay, let's delve into that because the reward is key. For summarization tasks, the paper states they use the BLEU score. That was introduced way back by Papineni et al. In 2002. They denote it as MSUM. Equal is BLEU, ICOMP Yorig. Why BLEU specifically? Why not something else like Rouge, which is also very commonly used for summarization evaluation? There are quite a few metrics out there.
That's a really perceptive question, and the paper provides a very clear and, I think, insightful justification for choosing BLEU. BLEU, at its heart, is a precision-based verbatim similarity metric. It works by looking at the overlap of n-grams sequences of words, like pairs, triplets, etc., between the summary generated from the compressed prompt compt and the summary from the original uncompressed prompt yorig.
So it checks if the same phrases are present.
Exactly. It helps to ensure a strong content similarity.
Mm.
And importantly, it helps minimize the introduction of inaccuracies or outright hallucinations in the summary generated from the compressed text. If your compressed prompt leads to a summary that has words or phrases not present in the original reference summary, BLEU will penalize that. It encourages faithfulness.
Okay, so it focuses on precision, making sure what's there is correct.
Right. And more critically, perhaps, and this is a key differentiator, they highlight BLEU includes a built-in brevity penalty. It penalizes summaries that are excessively long compared to the reference. This is vital because, as the paper points out, recall-based metrics, like some variants of Rouge, which focus more on capturing all the information from the reference, could potentially be exploited. A model could learn to just generate longer, more verbose outputs to achieve higher recall scores, a phenomenon sometimes called reward gaming, as discussed by Scals et al. In 2022.
So the model could cheat by just writing more, even if it's repetitive or irrelevant.
Potentially, yes. Imagine a model learning it gets a higher score just by generating a very verbose, rambling summary. A recall-based metric might inadvertently reward that behavior. By using BLEU, with its precision focus and brevity penalty, TACO-RL ensures more stable and robust training. The rewards are better calibrated. It prevents the model from learning these counterproductive shortcuts that don't genuinely improve the quality and, importantly, the conciseness of the summarization. It incentivizes accurate, faithful, and concise information transfer.
That's really smart. It prevents the model from just trying to inflate its score by being verbose or going off topic. Prevents gaming the system. Now, moving on to question answering QA tasks, the paper shifts its strategy. Here, they use the F1 score, denoted as MQA equals F1 weight compturig. Can you break down what precision and recall mean in this specific context for QA and explain why F1 is such a good, balanced choice for this kind of task?
Definitely. For question answering, precision and recall are defined very specifically to rigorously measure the accuracy and the completeness of the generated answer, your comp, against the reference answer, Jorgen. Think of it this way. Precision asks the question, of all the specific bits of information or tokens the compressed prompt generated as an answer, how many were truly correct and actually part of the original correct answer? Mathematically, it's the size of the intersection of the generated and original answers divided by the size of the generated answer. So if the model generates an answer, precision measures what proportion of its generated tokens are actually correct and genuinely present in the original correct answer. It's really about avoiding introducing wrong information, staying factual.
Okay, that's precision. What about recall?
Recall, on the other hand, asks a different question. Of all the truly correct information or tokens that should have been in the answer based on the original prompt, how much did the compressed prompt actually manage to capture and generate? Mathematically, it's the size of the intersection again, but this time divided by the size of the original correct answer. Comp. It measures what proportion of the original correct answer's tokens the model successfully managed to produce. It's about completeness, ensuring nothing vital is missed out.
So precision is about not saying wrong things. Recall is about not missing right things.
An excellent way to put it.
Right.
And the F1 score is simply the harmonic mean of precision and recall. It's chosen precisely because it elegantly balances both of these critical aspects. For QA, you don't just want to be precise, avoiding wrong info. You also want to be complete, capturing all the necessary info. You need both. A high F1 score acts as a reward signal that ensures the compressed prompt retains all the essential context required for generating answers that are both accurate and comprehensive. It pushes the model towards that ideal balance.
That makes a lot of sense for QA, where getting the full correct answer is key.
Absolutely. And let's look at a fantastic, concrete example from the source material itself. This really highlights the power of this task-aware compression using F1 for question answering. Imagine the question they tested. How many people per square mile lived in Fresno in 2010? A very specific, factual question.
Hmm.
Now, the original context provided for this question, as detailed in the source paper, is quite lengthy and comprehensive. Really verbose.
What kind of stuff was in it?
Oh, it included a wealth of information. Details about the 2010 U.S. Census itself, Fresno's overall population number, 494,665, its detailed racial makeup with specific percentages for various groups, white, African American, Native American, tons of Asian subgroups listed, Hmong, Indian, Filipino, Laotian, Thai, Cambodian, Chinese, Japanese, Vietnamese, Korean, Pacific Islander populations. It even broke down Hispanic or Latino populations by origin, Mexican, Salvadoran, Puerto Rican, and included historical notes about changes in the non-Hispanic white population since 1970.
Wow, okay. A lot of demographic detail, most of which isn't about population density.
Exactly. Much of this is utterly irrelevant to the specific question asked about people per square mile. Now watch what happens. When LLM, a task-agnostic compression method, remember it doesn't know the specific question being asked, attempts to compress this text, it produces something like this. I'm quoting from the paper. 2010 Census Fresno 1,665 for, 245,306 white, 40,960.3% African American, 8,525.7% Native American, 62,528 Asian, 3.6% Samoan, 1.7% Indian, 1.2% Filipino, 1.2% Laotian, 1.0% Cambodian, 0.5% Chinese, 0.4% Vietnamese, 0.2%, and Korean. Pacific Islander, 111,984. Other, 24,513, 2.4%. Puerto Rican, non-Hispanic, 30.0%, 72.6%, 1970.
Yikes. That looks messy, like a word salad of numbers and labels.
It does, doesn't it?
Yeah.
You can immediately see it retains many numbers and categories, but it's a chaotic, jumbled collection. It lacks coherent flow or structure. So when GPT 3.5 is then given this LLM lingua compressed text and asked the specific question, how many people per square mile lived in Fresno in 2010? What do you think it says?
I'm guessing it can't find the answer in that mess.
You got it. It responds simply. Answer not in context. A clear and frustrating failure. Why? Because LLM Lingua, being task-agnostic, couldn't discern which pieces of information were truly vital for answering this specific question about population density. It pruned indiscriminately, based on general statistics perhaps, and lost the needle in the haystack. The crucial number got thrown out.
Okay, so the generic method failed. How did TACO-RL do with its task-aware approach?
Now here's the contrast. TAC-ORL, guided by the F1 score reward for this QA task, generates what the authors call task-aware compressed text. For that very same question in original context, its compressed text reads, and I quote again from the source, 2010 census reported Fresno population 494,665. Population density was 4,404.5 people per square mile, 1,700.6 kilometers too. Racial makeup Fresno, 245,302%. White, 40,968.3%. African American, 8,525, 1.7%. Native American, 62,528.6%. Asian, 8.4%. Salvador, 0.4%. Puerto Rican. Non-Hispanic whites were 30.0% in 2010, down from 72.6% in 1970.
Okay, that looks much more readable. And, oh wait, I see it. Population density was 4,404.5 people per square mile. It kept the key sentence.
Bingo. Notice something critical here. Even though it still includes some details about racial makeup, it's not perfectly pristine. It didn't remove everything irrelevant. It clearly prioritized and crucially retained the phrase containing the answer. Population density was 4,404.5 people per square mile.
Okay.
So when GPT 3.5 receives this compressed prompt, guided by TAC-ORL's learning, what does it output?
It should get the right answer now.
It correctly yields the answer, 4,404.5 people. Boom. This stark contrast, I think, vividly illustrates the immense power of task-aware compression using the right reward signal. TAC-ORL knew what to keep because it was optimizing for the QA task's outcome, getting a high F1 score by matching their reference answer. It could surgically extract what mattered for that question. This is exactly the kind of intelligence that saves precious compute resources while actually enhancing accuracy. It's smarter compression.
That Fresno example really does bring it home. Seeing the actual text side by side makes the difference crystal clear. Task awareness is crucial. But, the proof in the pudding for any new method like this really lies in its empirical validation. Does it work consistently across a broad range of scenarios, not just one example? The researchers conducted extensive experiments on 3 diverse and challenging open-source benchmark datasets to thoroughly demonstrate TAC-ORL's effectiveness.
Tell us about these datasets and why they were chosen. Why are they particularly challenging tests?
Yeah, they didn't pick easy ones. They meticulously chose datasets that would truly push the boundaries of prompt compression, ensuring their findings were robust and generalizable, not just flukes. First, they used Meeting Bank. This is a dataset introduced by Hugh et al. In 2023, specifically designed for conversational summarization, summarizing meetings.
Meetings can be messy conversations. Exactly. This data set is notoriously challenging due to its complex, often nonlinear, and spontaneous dialogue. Imagine trying to summarize a sprawling, free-flowing meeting transcript. You have speakers interrupting each other, topics shifting abruptly, side conversations, unclear references. The contextual relevance isn't always immediately obvious. Traditional, simpler methods would really struggle to capture the essence here. Okay, that sounds tough. What was the second one? Second, they used Squad 2.0. This is a well-known benchmark developed by Rajpurkar et al. Back in 2016, designed for sophisticated question answering. Now, unlike broader summarization tasks, QA requires highly selective information extraction. You need to pinpoint specific facts. The core challenge here, especially in Squad 2.0, which includes unanswerable questions, is that different questions might necessitate entirely different, sometimes very minute segments of the same overarching context document to be retained. It's a nuanced challenge of pinpoint accuracy, not broad strokes. You have to find the exact phrase.
Right, different questions need different needles from the same haystack.
Precisely. And finally, they tackled Code SearchNet from Hussein et al. In 2020. This is designed for code summarization, generating natural language descriptions of what a piece of code does. This presents a unique, non-natural language challenge. Compression here demands the preservation of highly specific syntactic structures, the underlying algorithmic logic, and domain-specific semantic nuances within the code itself. You can't just randomly remove tokens from code like you might from prose. If you remove a crucial variable name, a parenthesis, or a keyword, you could completely break the code's meaning or functionality. Pruning indiscriminately would be disastrous.
Okay, so three very different beasts. Messy conversation, precise fact-finding, and structured code logic. Truly diverse and demanding benchmarks. How did they actually train Taco RL for these varied tasks? Was it like one single training run for everything, or did they take a more nuanced approach?
It was a very clever and, I think, effective two-stage training process. This really highlights their systematic methodology. Stage 1. Base model training. They began by training a foundational base model. This base model is structurally similar to LLM Lingo 2, using that Selm-Roberta large encoder. Importantly, it's initially task-agnostic. For the natural language tasks, Meeting Bank, Conversation, and Squad, QA, they use the large Wikitext dataset. This has a similar general English distribution, giving the base model a broad understanding of language structure and common patterns. For Code SearchNet, the code task, they specifically use the Pi150 dataset, which consists of Python code, tailoring the base model slightly more to that domain. This first stage ensures the base model has a general understanding of the relevant domain, text or code, and provides a good starting point for token classification, but without being specialized for any particular summarization or QA task yet. They train these base models efficiently for just 10 epochs.
So stage 1 gives it general knowledge. What happens in stage 2?
Stage 2. Taco RL fine-tuning. This is where Taco RL truly comes into its own, the special sauce. They then took this pre-trained base model from stage 1 and fine-tuned it using Taco RL's reinforcement learning approach. And crucially, during this stage, they incorporated those specific task-specific reward signals we just discussed. BLEU for summarization, F1 for QA, and likely BLEU again for code summarization, comparing generated summaries. This allowed the general model from stage 1 to adapt and specialize, learning the subtle nuances of each particular task. It learned what specific tokens were essential for Meeting Bank summarization, which different tokens mattered for Squad QA, and which code structures were vital for Code SearchNet summarization. It wasn't relying on generic rules anymore. It was learning from direct feedback on the task itself. It's like teaching a generalist doctor to become a specialist cardiologist, neurologist, and radiologist using feedback specific to each field.
That makes sense. A general foundation, then specialized tuning with RL. And for the experimental setup itself, the hardware, the models they used for comparison, what kind of computational power and setup were they wielding to get these results? That's always a practical question for our listeners, given how resource hungry these things can be.
Yeah, it's important context. They deployed a pretty robust setup. Definitely not something you'd run on a laptop. The backbone of their compression model, as mentioned, was the Selm-Roberta large architecture. That's a substantial encoder model with 561 million parameters, so quite large. All the experiments were conducted on a powerful compute instance equipped with 8 NVIDIA V100 GPUs. And these weren't small V100s. They each had 32 gigabytes of memory. That's significant computational muscle allowing for large batches and faster training.
8 V100s. Okay, serious hardware.
Definitely. For evaluating the performance of the compressed prompts downstream, they used GPT 3.5 Turbo 1103 as the target language model. They made sure to ensure consistency by setting the temperature parameter to 0.
Ah, zero temperature means a deterministic output, right? No randomness in the LLM's answers.
Exactly. It ensures reproducible outcomes, so they can be sure the differences they saw were due to the compression, not random fluctuations in the LLM's generation. During the fine-tuning phase, stage 2, they used a relatively small learning rate of 1e6, combined with the cosine annealing scheduler, which is a common technique to help training converge smoothly and effectively, avoiding getting stuck. And importantly, they established strong baselines for comparison. They didn't just compare TalkRL to nothing, they compared it against LLM Lingua 2, its direct predecessor, another method called selective context, and the original LLM Lingua. This provides clear benchmarks to really measure TalkRL's improvement.
All right, the stage is meticulously set. Powerful hardware, careful training methodology, strong baselines. Let's get to the results, the exciting part. What did they find for Meeting Bank, that challenging conversational summarization task? How much better was TalkRL?
The results for Meeting Bank, which you can see clearly summarized in Table 1 of their paper, are frankly really impressive. They speak volumes about TalkRL's effectiveness, especially in messy, real-world text. Get this, TalkRL demonstrated a performance boost of over 14% in BLEU scores at 2x compression. Let that sink in. They cut the prompt length in half, and the quality of the summary, as measured by BLEU, actually improved by 14% compared to the baseline compression method.
Improved quality with half the data. That's counterintuitive, but amazing.
It really is, and this boost became even more astonishing as they pushed the compression further. It climbed to a massive 45% improvement at 6x compression. So the prompt was reduced to just 1/6 of its original size, yet it was delivering vastly superior summarization quality compared to the LLM Lingua 2 baseline, trying the same compression ratio. And what's truly remarkable, almost the holy grail for practical applications, is this finding. At 2x compression, our model performance is close to the results with using the original contexts.
Wait, so half the prompt size gives almost the same quality as the full original prompt?
Essentially, yes. Maybe a tiny dip, but very close. This means you could potentially cut your prompt size, and thus your inference costs and latency, by 50%, and barely lose any summarization performance compared to feeding the entire bulky transcript to the LLM. That's an enormous gain in efficiency and a significant potential reduction in operational costs for anyone doing meeting summarization or similar tasks.
That is incredible. Having your prompt size for virtually no performance loss on complex conversational data.
Yeah.
Yeah, that's a game changer. Okay, what about Squad 2.0, the sophisticated question answering task that demands that pinpoint accuracy we talked about? How did TalkRL fare there?
For Squad 2.0, which, as we discussed, really demands highly selective context retention and precise answer generation, the improvements were arguably even more pronounced. It really showcased TalkRL's ability to hold on to that critical needle-in-a-haystack information. As depicted in Figure 2 and detailed in Table 5 within the paper, TalkRL significantly outperformed the LLM Lingua 2 baseline across the board on both F1 and exact match metrics. At a 2x compression ratio, having the context, it showed an improvement of 11% in F1 score, meaning the answers were better balanced in precision and recall. And even more impressively, a substantial 22% improvement in exact match score. Exact match is a very strict criterion. The generated answer has to be identical to the reference answer, character for character. Getting a 22% lift there is huge.
So more accurate answers and more perfectly correct answers with half the context.
Correct. And then, at the more aggressive 6x compression ratio, reducing the context to just 16% of its original size, these gains absolutely soared. We're talking an incredible 43% improvement in F1 score and a massive 63% improvement in exact match score, respectively. This clearly indicates a dramatic improvement in the model's learned ability to retain the truly critical QA information needed for accurate answers, even when under extreme compression pressure. It learned to be incredibly surgical in what it kept.
Wow. A 63% jump in exact match at 6x compression. That's stunning. It really learned what mattered for QA. Okay, one more benchmark, CodeSearchNet, the non-natural language challenge of code summarization, requiring preservation of those tricky syntactic and logical structures. How did it perform there? Was it as good with code?
So CodeSearchNet was interesting, even here where the authors noted that the initial task-agnostic base model from stage 1 actually performed quite poorly on its own. TalkRL showed remarkable resilience and delivered substantial improvement through its task-aware fine-tuning. As illustrated in Figure 3 and Table 6 of the paper, TalkRL delivered, and I quote, Gains ranging from 0.91x, which is 91% at 2x compression, to 1.89x at 5x compression in BLU scores compared to the LLM Lingua 2 baseline.
Okay, wait, 0.91x gain, that's almost doubling the performance, and 1.89x at 5x, that's nearly tripling the performance.
Essentially, yes. A 1.89x improvement means it's achieving almost 3 times the BLEU score of the baseline LLM Lingua 2 at that 5x compression level. It took a poorly performing base and significantly boosted it. The paper provides really clear visual comparisons of compressed code contexts in listings 1, 2, and 3, which are very illuminating. While LM Lingua 2's compressed code can often look like, well, a sparse and sometimes incoherent collection of keywords and symbols, maybe missing vital structure. TacoRL's compressed version, for example, for a Python function like Yixia download shown in the paper, meticulously retains crucial keywords like def, defining the function, variable names like hostname and SMID, the return statement, and important control flow elements such as if and elif blocks.
So it keeps the skeleton of the code intact.
Exactly. It strategically preserves the structural elements and the key identifiers that are absolutely critical for a human or another model to understand the code's purpose and functionality. This is unlike generic methods that might just strip away keywords or variable names based on frequency, potentially destroying the code's logic. This result showcases how TacoRL, guided by the summarization reward, likely BLEU here too, learns to retain not just content words, but also crucial syntactic structure and algorithmic logic, which is absolutely paramount for any code-related task.
So, to reiterate the overall success story here, TacoRL consistently performs exceptionally well across very different tasks, conversation, QA, code, and it does so across high compression ratios, up to 6x in some cases. And remarkably, as the paper notes, it often does so without even needing separate retraining for each specific compression level you might want at inference time. You train it once with guidance from SEA. And here's where it gets really interesting for anyone thinking about practical applications. It boosts performance by anywhere from, 8% to nearly 190%, almost tripling performance in some code cases, over previous state-of-the-art compression techniques like LLM Lingua 2.
The gains are substantial, yeah.
Yeah, these aren't just marginal improvements. These are the kinds of breakthroughs that could fundamentally reshape how we deploy and scale LM-powered services, making them faster and much cheaper to run. These kinds of efficiency gains, dramatically cutting costs and latency while often boosting accuracy, are exactly the kind of impactful developments the AI Coach by Anil Nathu aims to bring to your attention, helping you deploy more efficient and high-performing AI systems in the real world.
Absolutely. But, beyond just showcasing these really impressive headline results, the researchers did something else that's crucial for understanding why it works so well. They conducted several crucial ablation studies. These studies are like peeling back the layers of an onion, right? They meticulously remove or change one component of the system at a time, allowing us to understand which specific design choices and components truly drive TacoRL's superior performance. They provide invaluable insights into the why behind the numbers.
Okay, yes, ablation studies are key to understanding the mechanism. Let's start with the effect of different reward metrics. We already talked about why they chose BLEU for summarization and F1 for QA. Did the ablations confirm these were good choices? What happened when they tried other common metrics like Rouge 1 and Rouge L for summarization?
Yes, the ablations strongly supported their initial choices. As detailed in Table 2 and Table 7 of their paper, for the text summarization task on Meeting Bank, BLEU consistently led to superior performance compared to using either Rouge 1 or Rouge L as the reward signal during RL fine-tuning. This finding really reinforces their earlier reasoning about BLU being a more robust and less easily exploitable metric for summarization tasks in an RL context. Because BLU is precision-focused and includes that brevity penalty, it proves less susceptible to the reward gaming issue we discussed models just making summaries longer to boost recall. When the model was rewarded using Rouge metrics, which are more recall-oriented, the performance, as measured by other metrics like BERT score, not just Rouge itself, generally suffered. It illustrates the delicate balance needed in reward design. BLU just seemed better aligned with producing high-quality, concise summaries in this setup.
Okay, so BLU was indeed the winner for summarization rewards. What about for the QA task? Did they try alternatives to F1 score there?
They did. For the QA task, they explored various reward functions beyond just the standard F1 score. They looked at a more complex token-wise similarity reward. The idea here, intuitively, was to try to assign importance to individual tokens within the potential answer based on how similar the sentence they came from was to the original question. Seems plausible, right?
Yeah, like words from sentences similar to the question might be more important.
Exactly. They even tried combining F1 with this token-wise similarity reward, hoping maybe the combination would be even better. The detailed results are in Table 2 and Appendix D. However, the study yielded a really critical and perhaps somewhat counterintuitive finding. This seemingly logical token-wise reward actually degraded the base model's results when used alone. And even worse, it actually diminished the effectiveness of the F1 score when they tried to combine the two. The combination was worse than F1 alone.
Wow. So the more complex, intuitively appealing reward actually hurt performance.
Yes. This is such a profound insight for anyone developing RL systems, I think. It highlights just how sensitive these systems are to the precise design of their reward functions. A seemingly logical reward, conceived with good intentions, can actually be counterproductive if it somehow misaligns with the true task objective or inadvertently creates exploitable loopholes for the model to game the system in unexpected ways. It's a stark reminder that intuition doesn't always translate directly to optimal algorithm design in RL. You have to test rigorously.
That's a fascinating and crucial nuance. Okay, another component they tested. What about the effect of entropy regularization? You mentioned earlier that the ESHP term in the loss function was important. How critical was it really for the stability and performance of Taco RL? Did the ablation confirm its value?
Absolutely vital. The ablation study clearly showed its importance. As demonstrated in Table 9 of the paper, the entropy regularization term, HHP, was fundamentally important for ensuring stable training and for achieving better overall final performance. Models that were trained without this entropy term, effectively setting the weighting parameter to 0, consistently showed degraded results compared to the models trained with it.
So why is it so important? What does it actually do again?
It encourages exploration within the policy during the training process. It essentially adds a small incentive for the model to not be too certain about its keep-remove decisions, especially early on. This prevents the model from becoming too rigid or overconfident in its initial compression decisions based on limited experience. Without it, the model might quickly converge to a suboptimal local minimum, a strategy that works okay but isn't the best possible one, and fail to discover potentially much better compression strategies later in the training process. It's about finding that delicate balance between exploiting what you already know works, making high-probability decisions, and actively exploring slightly different options, keeping the probabilities less sharply peaked, just in case they lead to even better rewards down the line. Think of it as introducing a healthy dose of curiosity or randomness into the learning process, which is often essential for escaping poor local optima in complex search spaces.
Got it. Keeps the model searching for better solutions. Makes sense. And finally, what did they learn from the ablations about the impact of hyperparameters, specifically those two we discussed earlier, the compression flexibility controller C and the tolerance threshold L? How much do tweaking these knobs influence the final performance?
Figure 4 in the paper provides some compelling visual insights into the impact of these hyperparameters on the final performance metrics, like BLEU or F1. The researchers found that there's definitely a sweet spot and optimal balance for setting these parameters to achieve peak performance. They aren't parameters you can just set arbitrarily. The compression flexibility controller C, which, as we discussed, sets the target token retention rate during training, seems to have a particularly dominant effect. If C is set too strictly, aiming for way too much compression too early in training, or too leniently, not pushing the model to compress enough during training, the overall final performance tends to drop off. This highlights the importance of carefully calibrating this parameter to the task's needs and perhaps the difficulty of the compression. Similarly, L, the tolerance threshold for how much the actual compressed length can deviate from the target CX during a training step without incurring a penalty, also influences the results. Performance generally seems to increase up to a certain point with higher values of L, allowing more flexibility, but then could potentially drop off if L becomes too permissive, perhaps allowing the model to stray too far from the target compression too often.
So tuning is definitely required for best results.
Absolutely. These findings collectively underscore the immense importance of careful design, rigorous experimentation, and diligent hyperparameter tuning in all RL-based systems, but especially for something as sensitive and complex as LLM prompt optimization. It's definitely not a set-it-and-forget-it kind of endeavor. Achieving state-of-the-art results requires that continuous process of refinement and careful calibration. This practical reality is something that platforms like the AI Coach by Anil Nathu consistently emphasize in their practical guidance and strategies for real-world AI deployment. You need to experiment and tune. Now, despite its really impressive empirical performance and the significant advancements it represents, the authors of Taco RL are commendably candid and upfront about the model's limitations. It wasn't perfect. And it's important we acknowledge these, not necessarily as deal breakers or roadblocks, but more as exciting avenues for future research and development. Where can this technology go next?
Right. Understanding limitations points the way forward. So what are some of these key limitations they identified?
Okay, firstly, they reiterate something we saw in the ablations. The fine-tuning process itself is sensitive to the choice of reward function, base model, and task-specific prompts. End quote. As we just discussed, picking the right reward metric like BLEU over Rouge for summarization, or F1 over that complex token-wise approach for QA, profoundly impacts the final model's performance. Get the reward wrong, and it doesn't learn effectively. Moreover, the quality and the nature of the pre-training of the initial base model, stage 1, also play a crucial role. If your starting encoder isn't strong or well-suited to the general domain, even a highly effective RL fine-tuning in stage 2 might struggle to yield optimal results. The foundation matters. It means you really need to think carefully about and potentially experiment with the entire pipeline base model, pre-training data, RL algorithm, and especially the reward function.
Okay, sensitivity to design choices. What else?
Secondly, they highlight the intricacies of task complexity and dataset magnitude. Performance isn't guaranteed to be stellar on every conceivable task. The paper specifically points out that while TECO-RL significantly enhances performance for code summarization, this improvement diminishes markedly when transitioning from code summarization to code completion tasks, as shown in their results in Table 4.
Ah, interesting. Why the difference between summarizing code and completing code?
It's a subtle but incredibly important distinction, I think. For code summarization, the goal is typically to distill the high-level essence or purpose of a code block. What does this function do? You're looking for the core meaning, often expressed in natural language. You can often afford to lose some syntactic details. For code completion, however, the task is highly sequence-dependent and syntactically rigid. It requires generating the very specific next tokens at the end of a code sequence to form syntactically correct and logically executable code. If the compression removes even a single crucial comma, a brace, a parenthesis, or misspells a variable name right before the completion point, it can break the entire code's syntax and functionality, making completion impossible or incorrect. So the underlying compression strategy needed might be drastically different. For summarization, you're distilling meaning. For completion, you're preserving exact local syntax and executability. The current reward signals used, like BLEU on summaries, might not be sufficiently nuanced or appropriate for such fine-grained syntax-critical tasks like completion. They also mentioned another related issue. Extensive documentation strings, docstrings within code contexts could lead to reward manipulation by the model.
How would that happen?
Well, imagine a code summarization task where the reward is BLEU score, comparing generated summaries. The model might learn that simply retaining long verbose docstrings, which are natural language, helps it achieve a higher BLEU score, because those strings contain many of the words likely to appear in a good summary. It might prioritize keeping the docstring over keeping some crucial but terse lines of actual code logic, even if the docstring isn't truly essential for understanding the core functionality of the code. It learns to game the BLU score using the readily available natural language in the comments. This shows that constant challenge of perfectly aligning the reward function with true task utility, not just surface-level metric optimization.
That's a tricky problem.
Ah.
Okay, any other major limitations?
Finally, a very practical and honestly common limitation for many advanced AI models today. The fine-tuning process, that's stage 2 with reinforcement learning, is computationally expensive, requiring significant resources and time. While the inference phase of TACO-RL, actually using the trained model to compress prompts, is designed for low latency and efficiency. That was a key goal. The training phase to get to that highly optimized state demands substantial computational power. Remember those 8 V100 GPUs? They likely needed to run for many hours, possibly days, for each task and dataset to fine-tune the model effectively using RL. This is a common challenge with advanced RL methods and deep learning in general. Optimizing this computational efficiency for the fine-tuning stage itself is identified by the authors as a key area for future research. Making the training cheaper and faster would unlock even broader accessibility for techniques like TACO-RL.
Right. So sensitivity, task specificity issues like code completion, and the cost of training are the main hurdles. But it's clear that these limitations aren't really roadblocks, are they? They seem more like fascinating and exciting avenues for future research and development in this whole area of prompt compression. They provide a pretty clear roadmap for how this already impressive technology can become even more robust, more efficient, and more widely applicable across an even broader spectrum of AI tasks in the future. It's the natural cycle of research: solve one problem, uncover new ones to tackle.
Exactly. It's the continuous evolution of AI, always striving for better, smarter, faster.
So let's bring this home. After diving deep into the mechanics, the results, the nuances of TACO-RL, what does this all mean for you, our dedicated listener? For anyone out there working with LLMs day to day, maybe building AI applications, or even just staying curious about the cutting edge of prompt optimization, this deep dive into TACO-RL offers several incredibly actionable takeaways, I think. These can really inform your strategies and decisions moving forward.
Absolutely. Let's crystallize some key action points based on this research. First, and maybe foremost, prioritize task awareness. When you're looking to optimize LLM inference, especially for cost or latency, recognize the generic one-size-fits-all compression methods. Well, they might be a decent starting point sometimes, but they will likely be insufficient for achieving truly high performance and cost efficiency, especially on complex tasks. For cutting-edge results, you really need to prioritize solutions that somehow integrate task-specific objectives and provide direct real-world feedback on how well the compressed prompt performs your specific task. Don't just prune indiscriminately based on general statistics, prune with purpose and intelligence tailored to the goal.
Okay, task awareness is job number one. What's next?
Second, embrace reinforcement learning where appropriate. Understand that RL, particularly these on-policy methods like reinforce used in TACO-RL, can be incredibly effective, often superior, for aligning compression models with real-world task performance. It fundamentally moves you beyond simplistic heuristic-based approaches, like just removing stop words or low-entropy tokens that might easily miss crucial context or nuance. If you're building a system where accuracy on a specific downstream task is absolutely paramount, you should seriously consider leveraging RL to fine-tune your compression strategies, even if it requires more initial effort.
Makes sense. Use the tool that optimizes for the actual goal. Third point.
Third, and this cannot be overstated based on the ablation studies, strategic reward design is crucial. If you do go down the RL path, you must invest significant time and thought in defining robust, non-exploitable reward metrics that truly capture success for your task. As we saw, BLEU worked well for summarization, F1 for QA in their experiments, but a poorly designed reward function, even if it seems logical on paper, like that token-wise similarity, can actually hinder progress. Or worse, it can lead the model to game the system, optimizing for the metric itself rather than achieving true task success. You need metrics that genuinely reflect successful task completion for your application and avoid creating perverse incentives for the model. This might be the hardest part, actually.
Getting the reward right is key. Okay, number four.
Fourth, consider compression rate trade-offs wisely. TACO-RL clearly demonstrates that impressively high compression ratios, remember, up to 6x in their tests, can potentially be achieved with minimal performance degradation or sometimes even improved performance compared to weaker baselines. This means you don't necessarily need to make a harsh sacrifice between output quality and efficiency gains. Don't assume compression always means worse results. You should experiment rigorously with different compression rates, perhaps using C to guide training or just setting different targets at inference to find the optimal sweet spot for your specific use case, carefully balancing your computational budget, latency requirements, and desired output quality.
Find the right balance for your needs. Good advice. Number five.
Fifth, leverage bidirectional context in your models. Whether you're building a compression model or choosing one, recognize the profound value of using encoder architectures like BERT, Roberta, XLMR, that capture contextual information from both directions, left to right and right to left simultaneously. As we discussed, this allows for a much more nuanced understanding of each token's importance within the overall prompt. It significantly improves the model's ability to make intelligent keep-remove decisions and ensures it doesn't accidentally strip away critical information because it failed to grasp its full relationship within the broader text. It leads to smarter, more context-aware compression.
Use smart encoders. Got it. And the last takeaway.
And finally, a practical one. Prepare for resource investment for training. While the inference benefit of TACO-RL, the faster, cheaper prompts, is truly significant, we have to be realistic. Advanced fine-tuning with reinforcement learning, as the authors honestly acknowledge, does require substantial computational resources, GPUs, time, for the training phases. So if you plan on adopting TACO-RL directly or adapting similar cutting-edge RL-based techniques for your own compression needs, you need to budget accordingly for these potentially intensive training phases. The upfront investment in careful training yields those substantial long-term gains in operational efficiency and end-user performance downstream.
That's an incredibly powerful and practical action plan derived straight from the research. Prioritize task awareness, consider RL, design rewards carefully, tune compression rates, use bidirectional encoders, and budget for training. It's clear that the AI Coach by Anil Nathu platform continually analyzes exactly this kind of leading-edge research to provide you with the most effective, real-world strategies for deploying efficient and high-performing AI systems. This isn't just abstract theory, it's practical, cutting-edge advice derived directly from the forefront of AI research.
Exactly. So to sum up our deep dive today, TechORL represents a truly significant breakthrough in the ongoing challenge of optimizing LLM performance. By intelligently compressing prompts using task-aware reinforcement learning, it manages to dramatically reduce those traditionally high inference costs and frustrating latencies we talked about at the start. And it does this all without sacrificing performance and in many cases actually improving it compared to other methods. This is a genuine game changer, I believe, for deploying powerful LLMs much more efficiently and broadly at scale.
It really feels like a step towards making these powerful models more practical for everyone.
I think so. And as you, our listener, think about the future of AI and where this is all heading, maybe consider this provocative thought. How might these advancements in prompt compression, like AutoRL, not just make today's LLMs cheaper and faster to run, but actually enable entirely new kinds of applications? Applications where real-time responsiveness and extreme efficiency are absolutely paramount, maybe even non-negotiable.
Like what kind of applications?
Well, think about running sophisticated LLMs directly on edge devices, on your phone, in your car, in sensors where compute power and battery life are highly constrained. Or think about powering next-generation always-on AI assistants that need to react instantly without constantly hitting expensive cloud servers. This level of efficiency, where every single token pruned saves real resources, could potentially unlock possibilities that were previously just out of reach simply because the models were too big, too slow, or too expensive to run continuously or in constrained environments. Smarter compression might open entirely new frontiers for AI interaction.
That's a fascinating thought. Compression, not just as optimization, but as an enabler for new AI paradigms. Lots to think about there. Thank you for joining us today on this deep dive. Visit the AI Coach website for more AI insights.